All right. Thank you very much for this opportunity to talk here. I'm going to talk about AutoML, but actually almost exclusively about a subpart of AutoML, namely that's called neural architecture search. One note, so the slides are available, will be available. They are available in a slightly different format already here, but I'll upload the current slides there later on as well. And all the references in there are hyperlinked. So if you want to get any of the papers, you can just click on the PDF and directly get the papers. All right, so neural architecture search. Why are we talking about this? And it's because the choice of neural architectures actually really matters. So here we have sort of an evolution of the neural architectures used over the years, from AlexNet to Inception V4, and accuracy just keeps on going up over time. And that's not all. There's also this Pareto front. You want to do well in terms of accuracy as a function of the number of operations or the number of weights and so on. And neural architectures like hyperparameters are something that, a lot of people are working on manually. And the field of deep learning has really made big strides and has revolutionized machine learning, going from manual feature engineering to features that are automatically learned from data. But now the manual work has been shifted over from manual feature engineering to manual architecture engineering. And so the question there is, can we actually automatically design these neural architectures? And the answer is yes, we can. And that's what the field of neural architecture search is looking at. And this field is actually really exploding. So it's becoming this new focal point in the field of deep learning, because it's sort of one meta step further, trying to remove the manual architecture engineering and really learning the architectures that we then use in order to do our learning. So we wrote this survey in we wrote it in 2018, and then got published in 2019 when the field was still somewhat, could still be overseen, but there's really this exponential growth in publications. And it sort of all started going mainstream when there was this paper, Neural Architecture Search with Reinforcement Learning by Sof and Lee. I'm not going to talk much about this paper, only going to say that it was sort of a reinforcement learning approach that used a black box method using insane resources. So 800 GPUs for 2 weeks. That was a budget that they used in order to get somewhat state-of-the-art performance at C410 and PTB. And that was in 2016. And after that, people got really excited about neural architecture search. And nowadays, we're at neural architecture search methods that can actually find good architectures in a couple of hours on a single GPU. So I'm going to talk a little bit about this transition from there to here. And I'm going to talk about in particular 3 different parts. First, I'll talk about best practices and benchmarks for this very young community of neural architecture search research, where, not everything has been perfect. There's been some childhood issues, and that's why we need best practices and benchmarks for this field. Then I'll talk about speed-up techniques for NAS, and then some extensions of neural architecture search to different problem settings, in particular joint neural architecture search and hyperparameter optimization, and neural ensemble search, where we search for multiple neural architectures that achieve even better results than a single architecture. All right, so let's jump into best practices and benchmarks for NAS research. I mentioned that there's been some childhood problems in neural architecture search, like in many new fields of research. In particular, there's been plenty of evidence by several groups that in some cases, neural architecture search can actually give you poor performance compared to random search. There's definitely poor reproducibility, and even random seeds are very important. Sometimes something works with a particular seed, you get state-of-the-art performance, and with another seed, you get complete divergence. There's also evidence that the training pipeline matters much more than the architecture, so the hyperparameter is actually really important too. And there's been, no great scientific practices in field, and So availability of code has been extremely limited, and people couldn't really get into the field because of that. Also, of course, because of the computational resources. There was incomparable training code, search spaces, evaluation schemes, etc., etc. So you really couldn't compare two different works. And to give some more details of this problem that the training pipeline matters much more than architecture, here's an example from Young et al., likely 2020 paper. It's called, very good title, NAS evaluation is frustratingly hard, showing that actually the neural architecture doesn't make that much of a difference. So this here is 5 different neural architectures, having a spread of something like 0.5% accuracy on CIFAR10 in this case. And then they added all kinds of additional tweaks to the training pipeline of the final evaluation of the architectures actually stayed the same, and got a 1% improvement by adding drop paths, which is something like dropout on path through the network, then adding cutout, which is a data augmentation technique, adding further augmentation, and so on, to get in total something like 3% improvements just by playing with these tweaks, whereas the neural architecture only made up 0.5% of this. Of course, while this is the talk on neural architecture search, I don't want to diss neural architecture search completely, but there are some search spaces like this one where actually the neural architecture doesn't make all that much of a difference, and the hyperparameters are very important. Likewise, you often see tables in neural architecture search papers like this, where, well, these are just test errors from the different papers published in the literature. And, well, this is just very incomparable, as I mentioned before, because all these different papers use different training code, use different search spaces, use different evaluation schemes. So how well a method performs on CIFAR10 doesn't really directly tell you how well the method as such works as a meta-algorithm if you throw it on new search spaces and using new evaluation codes. And as a result of that, we came up with this NAS best practices checklist that basically is very much like the checklist for reproducibility by Joël Pineau for machine learning, which actually is required now for all ICML and NURB submissions. Not this particular checklist, but hers for reproducibility in machine learning. And in NAS, it's even harder because, well, there's code for the neural architecture search method. There's also code for training your neural architectures. Then there's hyperparameters of your neural architecture search method and hyperparameters of your neural architecture search training method. And if you have neither of these codes, then you just really can't compare the results of one paper against another. Then we also said one should properly compare the different methods. And in order to do so, it would be good to do multiple runs and to do statistical tests and so on. And of course, you can't do that with the computational expense that I mentioned earlier. Sof and Lee back then did a single run of the method, and that took 2 weeks on 800 GPUs. Nobody in their right mind would ask them to do proper comparisons with tens of runs and significance tests and so on against other methods, because, well, that just would just be really bad for the environment. And what we encouraged instead is to use these so-called tabular or surrogate benchmarks that I'll be talking about in the rest of sort of this benchmark part of the talk. And then also, actually, you should report important details, such as how much effort you put into hyperparameter tuning. Did you just run the method as it was, or in order to get it working, you needed like 1,000 outer loops around it? And one suggestion to NAS reviewers would be to de-emphasize these final results on CIFAR10 or PTB and so on, and be aware of these many confounding factors. All right, let me now start with this more scientific part about the different benchmarks that can be used in order to evaluate neural architecture search methods effectively and quickly. So the first of these benchmarks is NASBench 101. This is a relatively small search space that we actually exhaustively evaluated. And if you have a search space that is exhaustively evaluated, then of course you can run neural architecture search methods on that afterwards by whenever the neural architecture search method asks for the performance of a particular architecture, you don't train the architecture and evaluate it on the validation set, but you just look it up in a table because we've done all this computation ahead of time. And then you can actually do multiple runs, you can do robustness studies, statistical tests, etc., etc. You can do fair head-to-head evaluations by design because you just don't get to tweak the final evaluation pipeline or its hyperparameters because, well, those are just the numbers that are in the table. You take that degree of freedom away. And of course, source code and scripts are available. And we could only do this together with Google because the computational resources for this were insane. We used 4,000 TPUs for several months. And this was a conscious decision to put a little bit of strain on the climate for that once, in order to then afterwards actually have this be amortized very manifold. There's been hundreds of different groups working on this architecture data set before. Before it was published, people used it a lot. And often case, a single of these scientific studies would already take more compute than actually generating the entire data set. Because, well, you want to do multiple reruns and so on. And so you would query individual points in the table several times. And that way we did this one-time cost that is already far more than amortized. And you can, importantly, now also include scientific researchers in academia. You can run neural architecture search methods in minutes on a laptop in simulation, but still you can evaluate different methods now efficiently. So what this does allow you is to actually compare different optimizers, such as reinforcement learning from Sof and Lee, or random search. You can show that, yes, this is actually better and it's statistically better because here we actually did 500 runs and these are the means of these runs. And you see that things like regularized evolution and Bayesian optimization are actually also better than reinforcement learning in the end. And well, for example, Bayesian optimization here, the SMAC algorithm was published in 2011 and it actually does better than RL. But back in 2016, well, you couldn't ask Sof and Lee to actually evaluate that because it would have been another 800 GPUs for 2 weeks. So these tabular NAS benchmarks finally allow us to do proper scientific research. After NAS Bench 101, there's been a series of other tabular NAS benches. There's been NAS Bench One-Shot 1, which allows you to also benchmark neural architecture search one-shot methods. And so that's a subset of NAS Bench 101 that is sort of convenient and that one-shot methods work on. And I'll talk in a bit about what one-shot methods are. Then there's been NAS Bench 201, which is much smaller. It only has something like 6,500 unique architecture, but it looks at 3 different data sets, and you have the entire learning curves, so you can actually do prediction of learning curves, and you can do meta-learning across data sets with these 3 data sets. And then, just now we actually realized that, well, not realized, but now we actually tackled this problem that many of these NAS benchmarks, all these tabular NAS bench, are just too small to be realistic. And for example, local search is actually state of the art for all of them, but when you run it on large search spaces, it performs really poorly. So this is not the best proxy for real neural architecture search spaces. And so we set out to actually create the first NAS benchmark for a realistic NAS search space, namely the one of the popular DARTS method that I'll also be talking about later on. Now this one has 10 to the 18 different architectures compared to 10 to the 6 that we had in NAS Bench 101 and even less for NAS Bench 201. And this large space, of course, we can't cover this exhaustively. And so the way we got there is to actually fit a surrogate rather than a tabular benchmark. So how does a surrogate work? We observe a partial set of results. Actually, we collected 60,000 different architectures, and you fit a regression model to use that regression model instead of a table. And so when in NAS Bench 101 you would query a table, now you query a regression model that interpolates and to a certain degree extrapolates from your data. And the interesting thing to note here is that tabular benchmarks only have actually very few runs for each architecture. And well, they run SGD, and SGD is a stochastic algorithm. And so there's still error in these tabular benchmarks. There's still, if you want to evaluate a particular architecture, you only have something like 3 runs. And if you do this experiment where you say, well, what if my tabular benchmark was this 1 run here, and you compare it against the ground truth of the other 2 available runs, then you make a certain error in your tabular benchmark. And the amazing thing is that if you actually fit a surrogate on the available data, then you can actually, by virtue of the smoothness in the space of neural architectures, you can actually do better than a tabular benchmark, even when you have something like only 5% of the data of this NAS Bench 101, which had 420,000. So here with about 15, 20,000 architectures, we could already make better predictions than the table. And from a perspective of machine learning, of course, it makes a lot of sense that the model can do better than the simple model that would just look at an individual architecture and not care at all about other architectures that are similar, but only take the one noisy result from this one architecture. So we have the surrogate, and we use this just like a tabular benchmark. And how did we build the surrogate? Well, we tried to really cover the space. We had a lot of random configurations in order to globally cover the space, but then also looked at a lot of different NAS methods in order to also look at good parts of the space and sort of evaluate the space in the areas where we expect the NAS methods to actually go and evaluate a lot of methods. So we evaluated a broad range of different regression models to fit this data, and the best regression models turned out to be gradient boosting and graph convolutional neural networks. This is not a contribution of this work. We just took methods from the literature. But we showed that these can actually be used in order to define these surrogate benchmarks. And again, the estimation error is lower than the noise due to a single run of SGD. Now, when you have these surrogate benchmarks, you can use them in order to, well, benchmark NAS methods, and now not on a small space, but on this actual space of darts with 10 to the 18 configurations. And you can make plots like here, do one run of these methods that takes a long time, something like over like 10 to the 7 seconds. That is a lot of compute. And then you can do the same run on a surrogate, and you can see whether the result is sort of similar. And in the surrogate, again, you can actually do this run in seconds. And by and large, we got very similar performance using these surrogate benchmarks as for the true benchmarks. And you can also do things such as, well, let's run this an order of magnitude longer. Let's see what would happen then, that you just can't afford here because the runs are too expensive. Yeah, so this year was a single run would be over a GPU year, and here it would be seconds. All right, and yeah, you could only do one run here, and of course you could do many runs here in order to do statistical tests. All right, so to summarize this one part, that's more like the benchmarks and best practices part, is there are lots of benchmarks now. There's this best practice checklist. We actually ran the first neural architecture search workshop at iClear. And one thing that I didn't mention, we also worked on NASLib, which is a modular and extensible library for neural architecture search algorithms that finally enables empirical comparisons of these different methods without all the confounding factors by design. So this is sort of the coming of age part of the talk. There have been various problems from a scientific perspective that various groups rightfully pointed out, but the community has reacted, and there's all these things happening in the community that make me very positive towards the future of neural architecture search research. And it's really a good time to get into it. All right.
Can I ask a quick question?
Yeah, sure.
So I'm wondering for the surrogate methods, so say I want to build up a new surrogate method for another, say, speech and language data set. So in your experience, how many data points are necessary to give us enough confidence that we can build a good surrogate method?
Yeah, so
is there a way to think about this?
We use something like 50, 60,000, and that was good, but of course, we had to validate the performance of our different regressors on validation sets and did all kinds of different analyses. Well, what if there is weird architectures like this? What if there is weird architectures like this? Will it also fit this? Let's put some of these into the training set in order to sort of try to cover our bases. And we used a lot of different NAS methods in order to sort of cover different patterns that neural architecture search methods would look at, and in order to get the best surrogate that we can.
I see.
So I wouldn't recommend just taking the X architectures you've evaluated so far and making a surrogate and trusting it. I think it takes a little bit of design to make sure that it really covers the space well.
I see. Cool. Thanks.
And it's a first work on surrogates for NAS. Let's see if we've thought of everything, or if people start breaking it and show, oh, this surrogate didn't work for this particular case. Might be possible. So I would also say always go and check on the real data. One story that I didn't put into the slides is, after we did the first version of this, we actually ran local search from Colin White, the one that actually we had as motivation, that because it didn't work on darts, and we ran it, and with the same runtime, it also didn't work for us, but we let it run for longer, and then it actually became clear, state of the art, with an order of magnitude longer. So we actually let it run then in true for an order of magnitude longer, and it did become state of the art. So that's actually one way how we used it already to drive new research findings. And that's something that I could imagine happening in other cases too.
Thanks.
All right.
I have another question.
Okay.
So for your surrogate model or the tabular method, have you ever eliminated some outliers? There might be some architectures that might not work at all, that might be really poor performance.
So I will talk, for example, about one case where you have such outliers in this part here in weight sharing. Darts actually produces outliers like that. And if you don't take care of putting training data in those areas of the space where those outliers lie, namely architectures with a lot of skip connections or in the limit only skip connections, then you will not predict well there.
So you won't remove those points, you will just increase points near that point?
So you would put points like that into your training set so that your surrogate actually knows about what the performance is in that area of the space.
Okay, I see. Thank you.
Okay, so in the interest of time, I think let's move on and put more questions after the next block or at the end. Okay, so I'll go through speed-up techniques for neural architecture search along different dimensions now that get us beyond these 800 GPUs for 2 weeks. And well, for people who just want to get a general sense of NAS, this is actually probably going to be more interesting than this first talk that was more about, if you do research in NAS, this is really exciting, but if you just want to use it, maybe you don't care so much. So if you fell asleep, then please wake up again. Speed-up techniques for NAS. So the first one I want to talk about is about weight inheritance and network morphisms. A network morphism is an operator that changes the network structure from here, for example, to there, but not the modeled function. So for every input, the network still has to give the same output. And you can, for example, with this net to deeper net operator, achieve this by actually making this layer here an identity mapping. And then you have exactly the same function as before, but you have a different architecture. And this gives you now a move in architectural space that gives you basically pre-trained models that are pre-trained except this one layer. And this allows you fast architecture search via network morphisms. So if you have an architecture that has a certain performance, and then you apply different network morphisms, you, for example, make one layer wider, you add a layer, you add a skip connection, you always get exactly the same performance because it's network morphisms. It's the same function, so it's the same performance. And then you train for a little bit to actually improve the performance. You take the best one and iterate. And that actually, you just start this process with a relatively small architecture, and then you grow this architecture over time, and it gets better and better. The problem with that, well, the nice thing about this is that it enables quick architecture search, but the problem with that is that it only makes networks larger and larger. And actually, we would also like to have small networks that do well and do well in this Pareto front. So what we did for that is to extend this network morphism in an evolutionary algorithm to actually look at both the validation error and the number of parameters and move from this first generation that has this Pareto front over to actually in every iteration, in every generation, sort of push this to the left where we decrease validation error and to the bottom where we reduce the number of parameters. And this gives rise to this lemonade algorithm that is still relatively cheap. It's 1 week on 8 GPUs to actually give you the whole Pareto front. And we've run this with up to 5 different objectives at the same time. So it just sort of works out of the box. And yeah, you can compare this against previous mobile-sized networks that were manually designed, like MobileNet v1 and v2, and you can also compare it to NASnet, which is this neural architecture by Sofen Lee with reinforcement learning, and it does better when you use the same training pipeline. Again, you need this apples-to-apples comparison, and actually the training pipeline from these original papers from the NASnet is not available, so we can't evaluate against the original one, but with ours it's better. And this also transfers to ImageNet. So if you come up with these cell architectures for CIFAR10, then you can also plug these into ImageNet directly and also get better performance on ImageNet. All right, so that was weight inheritance and network morphisms. Now I'll talk about weight sharing and one-shot models, which is probably the most prominent way of speeding up neural architecture search these days. And here's sort of the one best known representative of this field, which is called DART's differentiable architecture search. So the space of architectures it looks at is where you have tensors here and these nodes of a graph, and these edges are the operations you use on these tensors. So this could, for example, be a skip connection or a 3x3 or 5x5 convolution or a max pooling and so on. So really, usually you have this discrete problem where you need to choose one out of these, in this case, 3 operators. But what DARTS does, it relaxes this discrete problem to get this continuous problem where each of these operations is applied actually in parallel, and each of them is getting an architectural weight alpha. So you have these individual operators and and you multiply them with these alpha vectors to get this mixed operator. And then these alphas, well, they are actually continuous, so you can then do gradient-based optimization to figure out what is the best operator in each of these different connections to solve this bi-level optimization problem where you try to find the best architectural problems such that if you train them with the best weight for this architecture, best weight as in the minimizer of training loss for this particular architecture, so you try to find the best alpha under this condition that you have the best parameters, the best weights for this alpha. And you simply do this, in this case, by iterating SGD steps on the validation set and the training set. And there's actually no guarantee at all that this converges, but it actually does well in practice. And then the last step is here, in the end, after we've run this bi-level optimization, you more or less take the most prominent edge on each of these arcs and make this your final architecture. You could also use this one-shot model, but the one-shot model is expensive in terms of the number of operators, in terms of memory and so on, and you discretize it to get a single architecture in there. And this is actually one of the steps that we'll show later is somewhat problematic. But first, some success stories will start. So we, for example, applied this to tune a vision pipeline for depth from stereo, where we have a left image and a right image here. And this is a competitor. And this is our method that directly gives you the lighter pixels are closer to the camera. So directly gives you the depth of a scene from stereo images. And with darts, we actually reduce the endpoint error over a previous state-of-the-art on the popular data set by 10%. So this just worked really well in this case. But in other cases, as we showed, it fails horribly. Actually, sometimes, quite often, it returns these completely degenerate architectures where in every step, it just picks a skip connection. So it's a network that only consists of skip connections, and it did this consistently across 4 different search spaces and 3 different data sets for us. And well, why is this the case? That's, of course, the big question. One might think, well, there's no theory about this bi-level optimization. Maybe that's a problem, but it's not. The bi-level optimization works. The validation errors continues to go down really nicely. But the test error goes down in the beginning, but then goes up a lot. And the interesting thing is that this goes hand in hand with the dominant eigenvalue, so the curvature in the architectural space going up over time. And so basically what happens is this optimization goes into an area of steep local minima in the architectural search space. And then you do this discretization step. And this discretization step is, of course, a relatively large step in architectural space. If you're already in a sharp local minimum, you move a certain amount of distance in this architectural space, you actually end up at something bad. Often, in fact, you have a lot of weight on these skip connections, and the skip connection is your most prominent connection, and then that's what you pick in every single connection. Some skip connections are useful, but only skip connections is really bad, and that's what darts picks here. And what we did in order to fix this is actually just add regularization to make your local minima not as sharp. So you could actually early stop, or you could regularize the inner objective, or by scheduled drop paths. It doesn't really matter. More regularization reduces this curvature and then leads to better performance. Sort of except on this one original space that was in the darts paper, which worked. And there's also a follow-up paper proposing a perturbation-based regularization that's even closer to the final step of darts that also gave really nice results. All right, so this is weight sharing in the one-shot model. Another way you can actually speed up neural architecture search is by meta-learning. And there's different ways of meta-learning. One way of meta-learning is this quite prominent approach by Chelsea Finn et al., where you actually have a task and you try to find meta weights, so initializations of your weights, to say if you have these weights and you allowed one gradient update steps in your inner task, then what is your performance? And that performance is actually your meta loss, and you do SGD on this whole thing. So you do SGD on your initializations of the network such that if for the various tasks you do gradient steps and you are interested in the performance after that gradient step. That is standard meta-learning. And how can you combine this with neural architecture search? Well, one way would be, as done in prior work, to wrap neural architecture search around that and say, well, you just evaluate the neural architecture such that in the inner steps you do this and you just wrap another loop around this in neural architecture search. But that is somewhat expensive. It takes over 100 GPU days. But instead, you could actually combine this. So in every step of this MAML approach, this model-based, model-agnostic meta-learning, you could update not only the meta weights, but you also update a meta architecture. So you have an initialization of both your weights and these alphas from darts. And then in the task learning, you do one step on the weights and one step on the architecture. So one step on the alphas and one step on the Ws. And then you compute your meta loss and iterate this. And this approach actually works really well and gives clear new state-of-the-art results. in the paper, we had this table that's sort of the table reviewers like to see. That's completely incomparable, but we do best. But we also have this result where we try to evaluate everything under the same training pipeline, the same hyperparameters, and so we also get best performance under those. And I would advocate to at least also have this table, and maybe this table is not so important, but reviewers want to see this table typically. So yeah, but this table actually costs so much engineering effort to actually really get the best training pipeline and the best hyperparameters. And I think that's why the paper got an oral, because reviewers like this sort of stuff. But this is a much better evaluation down here, I find. All right, so that's meta learning, how you can combine neural architecture search with that. And then finally, multi-fidelity optimization. So the key idea here is to use cheap approximations of an expensive black box. And this is something you can, of course, also do for hyperparameter optimization. And you want that the cheap evaluation, the cheap approximation of the black box correlates with the expensive black box. You could, for example, achieve this by taking subsets of your data, or by running fewer epochs of iterative training algorithms, or by downsampling your images, or by running short-term seed chains in Bayesian deep learning, or fewer trials in deep reinforcement learning. So all kinds of different approximations exist. And then the simplest method to actually apply there would be something like successive halving by Jamison and Tabular, which is visualized here for a budget of wall clock time. So you basically just start a bunch of different configurations or architectures, and then you stop the worst half and let the best half continue. Then, you double the budget, stop the worst half, let the rest continue, double the budget, stop the worst half, let the rest continue. And then in the end, you have something pretty good without having evaluated all these different architectures for this long amount of time. And we combined this successive halving, or the successor of hyperband, with Bayesian optimization, and that shows much better convergence in the end than successive halving and hyperband, because the one problem of successive halving and hyperband is that, well, they're based on random search, and we combine it with Bayesian optimization, so we would actually pick good architectures and raise these with the same approach that hyperband chooses. Fast forward to the results, we used this on top of darts in this application here, and got another 10% by actually optimizing the hyperparameters too, not only the neural architecture. And that already brings me to extensions of neural architecture search, which basically will follow up with an application of this multi-fidelity approach in the context of joint neural architecture search and hyperparameter optimization. So actually, joint neural architecture search and hyperparameter optimization is something we've already done back in 2015, before the Soft and Lee paper and so on, where we just basically ran Bob, or back then SMAC, on optimizing a deep neural network. And already back then, we actually won several data sets against human experts. For example, we had this one data set in a competition where we had something like 50,000 data points, 5,000 features, 18 classes. And this 2 months Kaggle-like competition where human experts could actually hit this data set with anything that they wanted. And we basically just ran what was then called AutoNet for a day on 20 GPUs. And it actually did better than all the human experts. So that goes to show that, well, deep learning is sort of flexible enough to want to be explored in an automatic way and not only by grad student descent. Nowadays, this has been merged into our Auto-PyTorch tool, and we also combine this with multi-fidelity and meta learning in order to actually be somewhat competitive in terms of speed. And this is already receiving quite a lot of attention in the community, which I'm very happy about. The search space is quite simple. So there's about a dozen parameters about the architecture and a dozen about the hyperparameters. And so far, this is for tabular data only. So the search spaces are not as complex as those for image data. Basically, it's some glorified feed-forward networks with skip connections. So resonance for tabular data, and parameterizations of these. And when you do multi-fidelity optimization with Bob, then actually, we used as a budget, we used SGD epochs and got sometimes quite nice speedups. You can only get a factor of 4 if the lowest fidelity is something like 4 times faster than the highest fidelity. But these factors of 4 we actually sometimes, always got in the beginning, and sometimes it didn't work in the end so well. Sometimes it was sort of as good or even a tiny bit slower than without multi-fidelity, and sometimes it just worked all the way until the end. They always give you better anytime performance. So the multi-fidelity here was not that important, but the meta-learning was extremely important. So meta-learning across different data sets, we actually achieved over 100-fold speedups here. So we looked at starting from configurations that worked well across a lot of different previous data sets. So look at a small set of 16 configurations that jointly cover a lot of the data sets. So if you pick the best of these 16 on a per data set basis, you want to pick the 16 that do best in that evaluation. And then those 16 we would actually raise in successive halving. And got something like 100-fold speedups. And compared to another baseline that would just have one setting for each of the configurations that work well on the previous data sets, that is sometimes not as good. Sometimes we're actually 100 times better than that too. So this Auto-PyTorch Tabular worked actually really well compared to AutoKeras, AutoScaLearn, HyperOpt-sklearn, even on tabular data sets. So that's somewhat surprising. Of course, we did some ensembling with some random forest and so on too, but actually that's the first time that the neural networks really do extremely well compared to something like AutoScaLearn. And we're currently running further evaluations on this. And also we were wondering if this also works on image data, and it does. So we ran this on NASBench 201, where we can do meta learning across these 3 different data sets in NASBench 201. So there we only had 2 meta-trained data sets to learn from, and nevertheless we got something like 10 to 100-fold speedups over running Bayesian optimization from scratch. And this actually made this then competitive with gradient-based neural architecture search. So actually, in this case, 4 times faster than the best gradient-based architecture search method that we evaluated. All right, so that brings me to the last point. So to conclude this point first, joint neural architecture search and hyperparameter optimization is definitely a good idea because the hyperparameters matter a lot. And you can also just tackle the hyperparameters along with the neural architecture if you, for example, use this multi-fidelity optimization. Moving to the second extension of neural architecture search, this is neural ensemble search. So this is motivated by the fact that ensembling often improves, of course, the performance of neural networks. And recent results show in particular strong predictive uncertainty estimation and robustness due to distributional shift if you have an ensemble. But actually, these ensembles here were so-called deep ensembles that are actually quite simple. It's just a single architecture with multiple runs of SGD and then put into an ensemble. And that they called deep ensemble, and showed that this actually is really state-of-the-art for predictive uncertainty and robustness to distributional shift. But the problem there is that, well, diversity tends to help ensembles, and these are not very diverse. They all have the same architecture. So we set out to actually look at different architectures for the different members of the ensemble, and, well, basically use neural architecture search to search for a strong ensemble of these diverse architectures. So here's a visualization of the predictions, and t-SNE encoding of the predictions of 5 different architectures, and you see that retrained 20 times with different runs of SGD, you get always somewhat, well, a cluster of predictions, and a cluster of predictions from this architecture, and from this, and from this, and from that. And so this goes to show that there is clustering, and that greater diversity might help. And here we have the same from one good architecture. And then we have individual architectures trained by our neural ensemble search, and we show that they're much more diverse and cover the space much better than an individual architecture would. And this basically then results in better performance of this ensemble. So basically looking at here, the deep ensemble of the best architecture that was found by neural architecture search, and looking at ensemble search, looking at more and more neural networks. And quite quickly, this actually surpasses the best architecture found in this case by regularized evolution as AmurbiaNet. Deep ensemble of that is often quite a bit worse than actually this neural ensemble search. And these differences are actually larger as you go to out of distribution predictions and uncertainty evaluation. Well, actually, sorry, this is the uncertainty evaluation. And out of distribution, it becomes even better. All right, that brings me to the end. So the takeaway is NAS is a field that's really coming of age. There's a scientific community forming around NAS, and it's a great time to actually join that field. And there's many ways to speed up neural architecture search. So we don't have this immense runtimes anymore, and can actually apply this now to all kinds of different fields. So if you're in field X and you would like to apply NAS, then now is actually a good time to start evaluating that. We also looked at different extensions, NAS and HPO and neural ensemble search. And yeah, there's slides and links to code and on this website, and we also have a book on AutoML. And with that, I would like to thank you, and I'll take some questions.
Frank, thank you for a very nice talk. Does anyone have questions or comments? Please do have.
Hey, I'll start with one. So this is a specific question about multi-fidelity. So I think you mentioned, for example, training on the subset of the data or running SGD for fewer iterations as a way to get a surrogate measure. I'm wondering, based on your experience, so how effective is this approach in general for different data sets, and how do you actually decide what subset of data or how much subset of data?
Yeah, that's a very good point. So in practice, actually, quite often there is more than one fidelity one could look at. There is, yeah, you could take a subset of data and do fewer epochs of iterative training algorithms. And yeah, the crux of the matter is that this still really takes a little bit of domain expert knowledge to, well, design budgets such that, and a budget could then be a combination of a subset of data and an epoch, that such that you get a high rank correlation between different architectures or hyperparameters when run on the one and run on sort of your expensive thing that you actually want to optimize. If you have a rank correlation of 1, then you can just exclusively work on the lower one and then take the best one and evaluate it on the largest one. But usually you don't have that. But if you have something like 0.9 or so, you're okay. If you have 0.4, then yeah, all these multi-fidelity methods don't really tend to work. So it's really, well, that's why approaches like hyperband have a guarantee that, you know, even in the worst case, if you have poor correlations, then you're still not much worse than starting with the largest one to start with. But well, that's not very satisfying in terms of giving you speedups. So I think one very interesting direction for the field is actually to work on automated ways of finding what are the right budgets to use. Should I use a third of the data or half of the data? How far can I push it? Can I push it to hundreds, thousands of the data where you really get these massive speedups? We worked on, I didn't talk about that, but we looked at SVMs where we actually got like 10,000-fold speedups by looking at subsets of the data. Because, well, SVMs actually scale superlinearly in the number of data points, so they're really prime example for doing multi-fidelity optimization, and the correlation was really, really high there. So there you could save a lot by not evaluating on the highest fidelity very often. But yeah, long story short, good point for future research.
But basically, you look at correlation as a way to figure out what's the right
Yeah,
thing to do.
so we look at correlation as a post-hoc analysis, but I think one could design algorithms that actually look at this online and change the budgets accordingly.
I wonder what's the largest data set you have used to build the architectures? Like I know for your NAS Bench 101, you used Cypher 10, which consists of 60,000 images, and actually compared to some data set we used in NLP, like for the data we used to train birds, that might be millions of points, and like the conclusions for NAS search you draw on a smaller data set might be totally different from a larger data set. And that raises another question that how would like the conclusions you draw on your tabular benchmarks would transfer to data sets?
Okay, so first conclusions, how do they generalize from small data sets, small as in number of data points, to larger data sets? We ourselves have actually not trained too many networks on ImageNet because, well, we're academia, we don't have the sort of compute that you're required to really get state-of-the-art on ImageNet. We've looked at some mobile nets for ImageNet, and well, ImageNet has 1 million data points, and but the community as a whole, actually, most NAS papers actually have the final architecture that you get on training on CIFAR 10 and evaluate that on ImageNet and tend to get state-of-the-art performance. Well, not tend to, but just in published papers typically just always do, because otherwise the paper doesn't get published. So there might be definite selection bias, but so that's I wouldn't actually be too worried about generalizing to larger data sets and larger in terms of number of data points and image resolution. Actually, ImageNet is also much higher resolution than CIFAR 10, and still the architecture is generalized. So I think that's not so bad. And therefore, well, the surrogates that we have, that we built specifically on CIFAR 10, on the Dart search space, I think will especially generalize to CIFAR 10 on the Dart search space, and just enable us to do the types of evaluations that people are doing every day on that particular benchmark much more cheaply and much more easily with reproducibility with many runs and so on. You could go and also build similar surrogate benchmarks for large data sets, and I actually expect that the community will do that now that we've shown sort of the methodology for how to build surrogate benchmarks. So I very much welcome that. I think the community has stuck with CIFAR 10 for far too long. There's actually another paper that I learned about recently that I didn't include in the talk yet. It's NAS Bench NLP. That is actually a small, I forget the benchmark that they used. Might be timid or something small from NLP that they have 15,000 architectures evaluated on. But I think nothing but compute would hold you back from building a tabular or surrogate benchmark for larger NLP tasks.
Okay.
Thank you. One more question.
Hello, I have a question about your tabular benchmarks. When you're interpolating between the different points, isn't that essentially a NAS method in itself? Because, I mean, if you think about like Bayesian hyperparameter search, you're basically running some approximate method to try and find the optimal method. So are you basically training a smaller, faster method using your bigger, slower method, which has more data? Is that some way you could think of that? Not really. The two are very connected, and it's always hard to
wrap this around your brain, that there's a lot of different methods in play. There's a method that the model that the neural network fits. There's a model, our surrogate model, that we use as a benchmark. And then there's the model that Bayesian optimization would use. And indeed, we use the same type of model for the model that's in Bayesian optimization and the model that we use in order to make the surrogate. There are graph convolutional neural networks that are used in Bayesian optimization. And so progress in one will help progress in the other. But when you run Bayesian optimization with graph convolutional neural networks on the surrogate benchmark, it doesn't get access to the 60,000 data points to start with.
Right.
It needs to select its data points, and well, it can do so for free rather than evaluating all the data points.
But I'm thinking this is more like kind of like teacher networks, where you have a really big network that's been trained. Like, because to some extent you would consider something that just brute forced every possible neural architecture search. It would just be super inefficient, and that's still something you consider. So it's like a neural architecture search, but of searching algorithms or something.
I mean, so the fact that this technology works to create benchmarks that can actually be used to benchmark different math methods suggests that these surrogate methods, surrogate models actually work well. And you could then go and say, well, let's train such surrogate models maybe on different benchmarks, on a whole lot of different data sets, and then use these models in order to, on a new data set, basically directly say, oh, I think this is going to work well. And so we could warm start Bayesian optimization, of course, with these 50,000 data points or with the model that we have here. And if we did that, it would just rock. It would work really well, but it would be cheating, right? That's not what, well, it would be cheating insofar that, well, somewhere I need to account for the time spent getting these 50,000 architectures. If you once and for all sort of cover a lot of different data sets, and then this just works for all vision data sets, and at some point, well, this is not cheating and it's perfectly fine. And this goes to show that there is predictability in this space and you can actually do well.
All right, thanks.
Okay. I'm afraid we are out of time, so if anyone more has any question, please contact Frank directly. Thanks all. Oh, thanks Frank once more for the interesting talk, and thank you all for coming and carefully listening.
All right, thank you.
Bye bye.